generation applications such as Sora, we call these models as artificial general intelligence. Based on the definition of Wikipedia or some large companies, we call AGI as a machine that possesses the ability to understand or learn any intellectual task that a human being can. And it has to basically mental abilities, like it can easily generalize to any task or some very difficult applications. And another thing is the AGI, it can have very common sense knowledge about the world, how the world runs and how the world reasons. So we call these things as artificial general intelligence. And in the future, we, in the end, want to reach the status of artificial super intelligence, which we imagine these things as the film, as in some movies like the Ultron in the Avengers and the Her movie in the Her. So I asked ChatGPT about, are you an agent with artificial general intelligence? And ChatGPT says, I am not an agent in the sense of having autonomy or independent action. And but it can. Oh, sorry. Wait a second. I need to share my screen. Sorry about that. Okay. So, but ChatGPT also knows that the general intelligence is kind of intelligence about self-awareness and some generalization ability. So today our topic is to apply how can we achieve the artificial general intelligence with the AGI agents, especially the applications in autonomous driving and robotics. To achieve this, we have many things to discuss about data, model, and learning, the typical things in deep learning and some modern artificial intelligence. So for data, we can have internet data, simulation data, and we can have manual action data. I have some examples below, like we can have some simulation data in this figure. It comes from the Wave demo and Tesla's demo. And we can have simulation data from some SimGen or any generation simulation tasks about days works. And we can have mobile Alaha to manually collect some data or some self-driving cars to collect data on the road. For the model part, we can have generation models such as some diffusion models to generate images and videos. We can also have autoregressive models to autoregressively generate some languages or even some images nowadays. We can have some amazing tasks, and we can also have some classic neural network models about CNN or transformers. For the learning strategy, we will use supervised learning, self-supervised learning, and reinforcement learning, whatever we can get to achieve the AGI for autonomous driving and robotics. And today we will have actually 5 amazing speakers from the autonomy and the robotics field. The first speaker is Kristen Roman. She comes from University of Texas at Austin. And next we will have Professor Chelsea Ping from Stanford. She will give a remote talk about humanoids and robot generates. And after that, we will have Devin Ramna from CMU to talk about some autonomous driving tasks. And we finally have Keshav Chita from the University of Tübingen and Chohao Sima from Shanghai to give a presentation about hands-on experience on Napsin GitHub repository and DriveLM project. So now I will give the stage to Professor Kristen Roman, and I will give a very brief introduction. So, Professor Kristen Roman is a professor in the Department of Computer Science at the University of Texas at Austin and research director in Facebook AI research. Her research in computer vision and machine learning focuses on video vision recognition and action for perception or embodied AI. Okay, Professor.
Awesome, thank you. Yep, I'm gonna share my screen with Zoom here. everything look good on? You want me to mute?
No. You need to be. Not sure why.
Okay. Like,
Okay. Oh, hi, Kelsey.
Hello.
Well, Professor Bing, could you hear us?
I can hear you.
Yeah, great. Okay. Our next speaker is Chelsea Bing. Professor Chelsea Bing is an assistant professor in computer science and electrical engineering at Stanford University. Her research interests lie in the capability of robots and other agents to develop broadly intelligent behaviors through learning and interaction. So please, Professor, please share the screen and we can start now.
I can't share my screen because someone else is sharing. Great.
All right.
Okay. Is the audio and video all good?
Yeah, we can see your screen.
Awesome. Okay. Hi, everyone. Really sad that I wasn't able to make it in person. Unfortunately, caught COVID late last week and still recovering from that. But yeah, there should be opportunities for questions at the end if you have any. So I'd like to start off this talk with some motivation around what robots can do today. And in some of my recent research and research in my lab and in collaboration with others, we've looked at whether robots can perform really challenging fine-grained dexterous manipulation tasks. And one work from a little over a year ago now, we were looking at teleoperation for really challenging bimanual tasks. And with this kind of puppeteering-like setup, we found that we were able to train policies to do fairly complex, precise tasks like tearing off a piece of tape and putting it on a box and putting a shoe on a foot. Then we tried to take that a step further, and instead of just looking at fine dexterous manipulation tasks on a two-arm platform, we looked at what about mobile manipulators? And we developed a teleoperation system for this mobile two-arm platform, which we called Mobile Aloha, also with a mix of puppeteering and kind of, in some ways, kinesthetic teaching or pushing the base around for full body control and teleoperation. And we also found that we were able to use this to collect demonstration data and then train autonomous policies with imitation learning to do, again, really complicated tasks involving full body control. On the bottom, there is putting a pot into a cabinet, and on the top, there's cooking a piece of shrimp. And these were some of the most complex tasks that we've trained robots to do to date. And beyond mobile manipulators, we also, in collaboration with some folks at Johns Hopkins, also looked at what about surgical manipulation tasks. And in some ways, the Aloha and Mobile Aloha systems were inspired by the Da Vinci surgical robot, but of course at a much smaller cost. And again, we found that if you collect demonstrations on this platform and train with imitation learning, you can get policies that can actually do pretty complicated things on this platform, including tying a knot and picking up a needle with various distractors. So one of my takeaways from this is that if you can teleoperate a robot to do something, then very likely the robot can actually learn it. And I think that's actually fairly powerful because it suggests that if we want a robot to be able to do a particular task, then we should, if we can find a way to teleoperate it, then we have a path towards that task being kind of solved in some sense of the word for that task. So I think that that's one takeaway. Now, of course, there's a lot of really challenging open problems, and a couple that I wanted to highlight is that first, there are systems where it's really challenging to do teleoperation, such as if you have like humanoid systems that you want to control the whole body of, then teleoperation is very difficult. And second is even if we can train a policy to do one task in one scenario, actually getting policies that are robust to lots of different scenarios, distractors, different environments, and so forth, remains really challenging. And so these are the two things that I'd like to talk about today. Can we advance teleoperation, and can we look at training generalist policies? So this first one, let's talk specifically about teleoperation for humanoid robots. Now, I guess as some background before we dive into developing like a teleoperation system for humanoids, it's worth acknowledging that there's a lot of prior work on trying to control humanoids, including with model-based control. Here is a video on the left on the Atlas robot, and also using sim to real by training a policy and purely in simulation with reinforcement learning and then transferring the policy to the real world. Despite these successes and the kind of the really impressive progress we've seen from these kinds of robots, techniques in model-based control remain somewhat brittle to different circumstances. And for approaches that try to use entire sim-to-real transfer with reinforcement learning, you often learn policies that are task-specific. And in this particular case, it's relying very heavily on pose estimation of objects in the environment rather than learning from camera images and other sensors on the robot. So one motivating factor is that humans have a lot of general skills. Maybe we can kind of transfer from human behavior directly to humanoids. And if you try to just take kind of train a policy on humans and directly apply that to a humanoid, that doesn't work. There's kind of different actuation strength, mechanisms, responsiveness, and so forth between humans and humanoids. There also are some differences in morphologies, like the number of degrees of freedom, the length of different links of a person versus a humanoid, height, weight, and so forth. There's also different parameters and mechanisms for being able to see. And of course, gravity can play a large role in terms of needing to be able to balance and stay upright and so forth. So instead, what we're going to do is we're going to try to actually train a shadowing policy and then use that for a teleoperation instead of trying to directly mimic human data and directly copy joints from human data. And the way that we're going to do this is we'll take the AMOS data set and retarget it to kind of the human poses and the hand poses to our robot. Then what we can do is in simulation, we can train a policy that conditioned on the retargeted pose, basically the desired pose that we want the robot to accomplish, we'll train a policy to try to match that. And that isn't trivial because it needs to try to match that while also not falling down and obeying various physical and dynamic constraints in the environment. And so we'll do this with reinforcement learning. And again, there's a policy that's trying to match any input pose that is provided to the robot. And specifically, we'll train an architecture that uses a transformer and is conditioned on the target poses and outputs the torques to try to match the target poses. Cool. So we'll do this in simulation, and we'll use domain randomization in simulation in order to be able to transfer this shadowing controller to the real world. And to deploy this, we will basically have an RGB camera that's looking at a person. We'll use existing models for hand and body pose estimation, and these are from these really excellent prior works here. We'll then retarget the human pose to the robot pose, and then use our controller to control the robot to try to match that targeted pose. And so this part is the part that is trained in simulation, whereas these other parts are using like off-the-shelf models and run at test time. Cool. So this is the result of that shadowing system. And so on the left is the person that the robot is trying to shadow. And we're using a single RGB camera here. And the robot controller, we can see with some delay, is able to follow the human that it's shadowing right here. And what's cool about this is you can actually do lots of different things. It's reactive to the poses that the human provides in real time. And then we can do this for pretty precise tasks, including typing, playing a piano, and we can do it for tasks that require full body control. So tasks that require using both hands, tasks that require reaching out the arms in front of the robot, which requires a great deal of balance, and also tasks that require needing to squat or get up out of a chair and so forth. In comparison to other approaches for trying to teleoperate this robot, we tried to teleoperate with a few different other approaches on rearranging objects, and shadowing only requires one person. If you try to use kinesthetic teaching to move the arms, it requires multiple people. Likewise for an approach like Aloha or using Oculus controllers. Only shadowing in comparison to these approaches is able to do teleoperation for the whole body and actually prevent the robot from like falling down, for example. It is actively maintaining balance while shadowing. And we also find that we're able to actually teleoperate faster with shadowing than these prior approaches. So generally it's easy to use. It allows full body teleoperation, and it's also inexpensive. You only need an RGB camera. Now, we also compared the shadowing controller to the default H1 controller, which is pretty robust. And we found that if you apply force if you apply large forces, the robot is actually able to maintain balance more effectively than the default H1 controller. And we're also able to use it to squat lower than the default controller, jump higher, and to be able to stand up from a sitting position. Cool. So once we have the shadowing system, we can actually then use it to collect demonstrations in the real world for imitation learning. And this means that we can, by means of collecting data in the real world, it means that we can also collect data from all of the robot sensors, including real RGB images, and with everything that comes with the fidelity of the real world. And so we're going to collect around 40 demonstrations per task. And then we're going to train a transformer to match the collected demonstrations from the shadowing system. So the inputs to the model are 2 cameras from the head of the robot, as well as the proprioceptive information. We'll pass that into the transformer alongside positional embeddings. And we'll train it both to predict the target poses with action chunking to predict the target poses into the future. And then we're also actually going to be predicting, as a regularization, we're going to be predicting the features from future images. We found that this helps prevent overfitting, especially to the proprioceptive data. It encourages it to use the image data, which is really important for solving the task. And we found that binocular perception can be helpful for depth-sensitive tasks. Cool. So here's the autonomous policy on the robot for 5 different tasks. This first task, the goal is to put the can into the basket on the other robot. Here's a jumping task, which is quite challenging to do. Here is a folding task for a somewhat low fidelity fold. But again, this is a task where you actually have to actively maintain balance as you're moving the arms forward, which is somewhat challenging, especially just in a static standing position. Here's a task of rearranging objects into a basket, a precise task of typing AI on a keyboard, and a task of kind of giving a light handshake to another robot. Quantitatively, we found that the success rate of the autonomous policy on the task is 80 to 100%, so pretty high success rate. We see a 10 to 60% improvement from using binocular vision. So some tasks we find it to be quite helpful, like folding clothes and typing AI. Other tasks it was less important, like and intuitively so, like the 2 robot greeting, for example. It's a little bit less important to have really accurate depth perception. We found that regularization helps for precise tasks. And so if you compare ACT and HIT, you see a really large difference for typing AI, which is a pretty precise task, and a smaller difference for other tasks. And lastly, a fully open loop policy really struggles to perform this task. And it's reflective of the fact that you do need to, it's important not just to copy the demonstrations, it's you really need to actually react in real time to things that are happening. Cool. So the takeaways for this part is that large-scale reinforcement learning and simulation can allow us to train a task-agnostic shadowing policy. And shadowing for teleoperation of demonstrations is low cost, intuitive, and allows us to collect demonstrations that are effective for imitation learning that allows us to learn full body control on the humanoid in the real world, which is pretty cool. Also, the code from the project is available online. Cool. So that was a step towards trying to advance teleoperation and allow us to collect demonstration data for more complex form factors like humanoids. Now I'd like to talk about trying to expand the scope and the generalization of policies learned with imitation learning. In the humanoid project and in the other projects that I showed, the policies are kind of narrow in scope. They're trained on one environment for one task. And ultimately, many use cases we might care about a policy that is robust to many environments and can perform many tasks, and potentially also be able to control many different embodiments. Great. So this brings me to give a little bit of background on generalist robot policies. And two works that I was quite excited about were the RT2 policy and the RT2X policy. So first, RT2 was a policy that used a pre-trained vision language model, specifically the poly-X model. And it found that if you take this pre-trained vision language model and then fine-tune it on a large amount of robot data, then you get really strong visual generalization. And specifically, the policy is able to generalize quite effectively to scenarios with new distractors, scenarios with different textures of the background, with different lighting conditions. And it also allows the policy to handle instructions that refer to object categories that the robot hasn't seen in the robot data before. So this result was really exciting to see how you can actually really translate kind of powerful vision language models and a lot of their knowledge and generalization and kind of imbue that to robots. And so this was kind of introduced the term vision language action model or VLA model, specifically basically a VLM that's then trained on robot data. And then from there, the RT2X work showed that you can actually train a policy not just on one robot, but also train on many different robot platforms and data sets. This is using the same architecture and recipe as RT2, but trained on more robot data covering more robot platforms. And RT2X was really exciting in my mind because we actually found that you can send a checkpoint over to multiple labs and actually just have them run that checkpoint on the robot, and the policy would actually work better in many cases than the policy that was developed specifically for that robot platform in that lab. So from here, one of the things we wanted to study is whether we can take an open source vision language model and match the performance of this really strong RT2X model. And I should note that RT2X is a 55 billion parameter model that builds upon a proprietary vision language model at Google. And we're going to try to use an open source 7 billion parameter vision language model in our work and try to develop an open source vision language action model and see what it takes to try to develop something that's about as strong as RT2X. So this led to the Open VLA project. We started with a 7 billion parameter vision language model with a VIT encoder and Llama 2 as the base language model. And then we're going to fine tune it on robot data. So for example, we'll take an image from a robot camera here, feed that into the vision encoder. Then we'll also take a language command and feed that into the vision language model as well. This will then produce action tokens, which will detokenize to predict the translation and rotation and gripper motion on the robot to solve the task. So getting into some of the details, we started with the prismatic 7B VLM. And so this VLM uses a fused vision encoder of both SIGLIP and Dino V2. We're then going to project the embeddings to the input space of the Llama language model. And these tokens will be passed alongside language tokens from language instruction into the Llama model, and then output tokens for the actions. Then we'll convert these tokens into the continuous translation, rotation, and gripper position to execute on the robot. This model, we're taking an image and a language instruction at every time step and outputting the corresponding action. So we're actually running this in closed loop. And then prior works found that vision language models, oftentimes you can actually just freeze the vision encoder. We actually found it really important to fine tune the entire model, including the vision encoder end to end on the robot demonstrations. We fine-tuned it on 970,000 robot demonstrations curated from the open cross-embodiment dataset. And this is data that covers multiple different robot platforms. And then we trained the model on the robot data on 64 A100s for 15 days. Unfortunately, my lab does not have anywhere near this kind of compute. And so we used this was in collaboration with researchers at Toyota Research Institute, and they were generous enough to provide the compute for this training run. Cool. So those are the details of the model. We looked at two different evaluations. One is out of the box. How well does the model perform on robots that are represented in the training data? And we're going to compare both to open source generalist policies, specifically RT1X and Octo. And we trained, the RT1X and Octo are trained on subsets of open cross embodiment, just like OpenVLA. But the key thing is that they don't use a pre-trained vision language model. They might use pre-trained encoders, pre-trained embeddings, but they're not going to really get all the juice that you get from a large pre-trained vision language model. And then second, with some help from Google, we'll also compare to the RT2X model, which is a closed source and proprietary model that's much larger than our model. The robot data covers many different robot platforms, but we're going to evaluate specifically on two of them. One of them is the WidowX robot following the bridge data setup, and another is, with some help from Google again, evaluating on a Google robot. And then lastly, we're really going to focus the evaluation on generalization, because this is where we might expect to see some benefits from using a pre-trained vision language model. Great. So in the results, the first thing that we can notice is that the green and red lines, the two VLA models, are a lot stronger than the other generalist policies in blue and orange. And so this means that we're getting really strong improvements from VLM pre-training along these different axes of generalization, like visual generalization, motion, physical, semantic, and language grounding. And we also see that OpenVLA is actually stronger than RT2X on average, both on the WidowX robot by a really 20% margin, and by a much smaller margin on the Google robot. This was somewhat surprising, especially because the OpenVLA model is a lot smaller than the RT2X model. And it's a little bit hard to attribute very specific design choices for why it might be better, because we aren't able to run a huge VLA training run multiple times. But there are a couple of things that might be better. One is that the language model likely isn't stronger, but the encoders, the visual encoders, the SIGLIP and Dino V2 encoders, that fuse encoder might be stronger than the visual encoder from RT2X, which is about a year old at this point. And the second is that there is more robot data that the field has open sourced. And so we might be getting more juice out of that additional data. We also did a little bit of curation on data from the bridge data set to remove actions that were all zero. And that curation might be adding to performance as well. Cool. And then beyond just evaluating the model zero shot out of the box, we also looked at whether we can fine tune to new tasks, which is important because we might care about looking at tasks that aren't tasks that are like very different from things that are represented in the training data set. We're actually going to do this on a third robot platform to emphasize the generality of the model, and we'll compare it to fine-tuning the Octo model, as well as to diffusion policy, a state-of-the-art imitation learning method trained from scratch. And we'll compare to diffusion policy with and without bells and whistles, since there are some design choices like action chunking, using absolute actions, and so on that diffusion policy includes, but OpenVLA doesn't include and could probably benefit from. Great, and then in our experiments, we found that on narrow tasks, training from scratch was quite strong, especially with the bells and whistles in purple. And diffusion policy was generally performing quite well on these narrow tasks, whereas on more diverse multi-instruction tasks and on tasks requiring visual robustness, using a pre-trained model is quite helpful, and OpenVLA specifically is able to provide the strongest performance when fine-tuned on these tasks in red. So this means that it suggests that, especially when you're fine-tuning tasks that might require a little bit more generalization or a little bit more ability to handle different instructions, OpenVLA is a really strong contender for using kind of a pre-trained model for these tasks. And then one of the other experiments that we ran is when we did the full training run of taking a VLM and training it on robot data, we didn't find parameter efficient fine-tuning methods to work well for that sort of for that part of training. But we did find that if we take VLA and then OpenVLA and then fine-tune it on new tasks, LoRa is quite feasible, and we saw somewhat comparable performance when using LoRa when we had a third of the VRAM and many fewer parameters that we're fine-tuning. Cool. So the takeaways here is that we have a state-of-the-art robot foundation model that's fully open source. It outperforms RT2X despite being almost 10 times smaller, and we see efficient fine-tuning to new tasks. The code and the weights are open source on Hugging Face, and so we hope that it'll be a useful resource for the community, both out of the box potentially, as well as when fine-tuned to new tasks. Great. So I guess to summarize a little bit, I talked about this takeaway of how we can learn a lot of things if we can teleoperate it. And I talked about how we can enable teleoperation for more challenging whole body control tasks, and talked a little bit about trying to scale data and trying to scale pre-trained models to train more generalist policies that aren't just good at one narrow complex task, but for many different tasks. Along the veins of training generalist policies, at Pi, we're also looking at how we can scale up robot foundation models to tackle a wide range of real-world use cases and robot platforms. And here are a couple videos of some things we've been up to over the past few months. And yeah, like to really highlight the students that led the work that I presented. Zipeng, Chiching, and Chi led the humanoid work, and Mujin, Carl, and Sid led the OpenVLA work. Happy to take questions.
Thank you, Professor Bing. Okay. Are there any questions from the audience? Maybe you can just, to simplify, you can just go to the front and use this mic. Next one.
Hi, thank you for your talk. Why did you use a combination of SegLab and Dino V2 and not either one of the two?
What was the alternative that you mentioned?
Sorry, can you repeat that?
You said, why did you use SegLab and Dino V2 instead of something?
Instead of either one of the two, so you use both.
Yeah. We found in kind of somewhat preliminary in experiments on like a smaller scale version of smaller scale experiments, like when we were fine-tuning on a single robot data set, a much smaller robot data set, we found that combination seemed to perform the best. But and certainly using both, we have plenty of data to be able to accommodate the larger model. So yeah, we ran some smaller scale experiments where we found that to be best. So mostly an empirical choice.
Okay, interesting. Thank you.
So thank you for the great talk. Hello, thank you for the great talk. I wanted to ask about the embodiment where those like generous model usually have to be fine-tuned before they deploy on the like new robot like embodiment. What do you think about the like challenges in this direction?
So you're asking like, what do I think about the challenges of like when you have to fine tune rather than deploy the VLA model zero shot?
I think my question is about the like generalization capability of the robot foundation model in terms of the embodiment.
I see, yeah. So definitely, I think that if you have an entirely new embodiment, I don't think that we can expect the model to work completely like on out of the box on time step 0. I do think that we've seen really substantial like in context learning abilities from foundation models, and I could definitely imagine a future where you can adapt to a new robot platform in context rather than having to fine tune. Essentially, you need to understand how robot actions will affect that robot embodiment. So yeah, I think that there's probably potential in the future for in-context adaptation. Right now, we definitely just need fine-tuning, certainly. And I also think that fortunately there aren't that many robot embodiments, and typically it's not that expensive to collect some data on a robot platform. Even just like a day of data can go a long way for being able to learn something about that robot embodiment.
Okay, thank you so much.
Thanks for the talk. What do you think about the debate between humanoids with 2 legs and maybe 5 fingers versus like wheels and 2 fingers?
Yeah, great question. I think humanoids are cool. I don't think that I think that there's a lot of benefit to simplicity and a lot of benefit to yeah, simplicity, low cost, and being able to teleoperate a system as well. As we've seen, teleoperating humanoids is definitely harder than teleoperating a mobile manipulator, and we saw that in our work too, between like mobile Loha and the H1 humanoid. So I think that ease of teleop and simplicity are really not to be underestimated, and generally from a practical standpoint, I think I would always opt for the things that are simple, especially if they allow for a really substantial amount of capabilities, and if they allow for ease of teleop, because ease of teleop will translate into more data, and data is really useful. Yeah, that said, I think humanoids are cool. I also think that in the long run, we should have models that should be able to control any robot embodiment, including humanoids, if we have data for them. And so we don't necessarily need to pick between any one platform.
Thank you.
Okay, due to a time limit, we may accept 2 more questions.
Hi, I had a question more on the teleoperation, especially the humanoid teleoperation from the camera that was external and getting poses. I know you showed that it was cheaper because you can just do it to one person and it's faster. But how much do you think some of the amazing, especially fine manipulation from Aloha and those systems comes from the kinesthetic teaching and the ability to like really finely control the system? And do you think just using some sort of targeting would really help with those sort of skills, because the humanoid skills that you showed were more towards the gross end of the spectrum with large objects? Just your thoughts on that.
Yeah, I mean, I definitely think that ease of teleop, like I was mentioning in the previous question, is a huge advantage for collecting data. I think that you shadowing, because of the latency and the distance you are from the humanoid and so forth, and also the hand that we're using only has 6 degrees of freedom, whereas our hands have far more degrees of freedom than that. It definitely makes for a less intuitive experience compared to like teleoperating something like mobile Aloha. So I think definitely we have a ways to go in terms of teleop for humanoid systems. And I think that generally like puppeteering systems, exoskeletons, that sort of stuff, where you can get like, it seems like you can get really precise motions from that. Definitely seem really promising to me. I think we should still do research on all sorts of approaches, of course. But yeah, I think that like puppeteering approaches in general are extremely promising. Yeah, especially for like really precise tasks.
Thank you.
So thank you for the great talk. I had a question about like in the initial stages when you start this work, is there like a simulation environment to sort of first work with it, or someone who wants to get started, is there like a smaller scale that they can start at without actually, buying a large robot?
Yeah, great question. Definitely for the humanoid project, we basically just started, well, I guess for both projects, we involved simulation, early on, like, some of our initial experiments for the Open Relay project, we took a simulator and we're making sure that we could like do a task in simulation, because if you can't do a task in simulation, you're definitely not going to be able to do a task on the real robot. And so there are ways to get started with that. We often use like the Majoko physics simulator, which is free to use. There's also various benchmarks that have tasks that are set up, like Libero is one of them that's fairly popular right now. And then on the humanoid side of things, we're starting in simulation as well. And yeah, and definitely I really like using real robots and validating that things work in the real world, because if you get something to work in simulation, oftentimes it doesn't work in the real world yet, and you have a lot of work to do to get it to work in the real world. But simulations are quite accessible, and in both of these works we did initial debugging tests in simulation, and yeah, before moving things to the real robot.
Thank you.
Okay, let's thank Professor Josephine again. Thanks for the great talk and hope you will recover soon. Thank you. Thank you, Professor.
Thank you.
Okay, we will have a short break, maybe 5 minutes, and we will return back in 10:40, and we will have the talk from Professor Deborah Rondon from CMU. Thank you.
谢谢他。然后让他测一下有没有 video audio。
有呀，现在都打。
我让他试一下麦。
麦自己试就好，我自己试。没有声，他没有，本来就没有声。他说没有 audio。
check check。Welcome back. Okay, for the next speaker is Professor Deborah Remno. He's a professor in the Robotics Institute at Maryland University and the former director of the CMU Center for Autonomous Vehicles Research. His research interests span computer vision and machine learning. His topic today is learning to plan in a reactive world. Let's welcome Professor.
Thank you very much. So let's get into it. So the framing of the talk will be, I think, the framing of this workshop in some degree. How do we enable foundational innovation for robotics and particularly self-driving research, autonomous vehicles? And I'll start out with this, I think maybe not controversial claim for this audience here, but just like we've seen this transformational power of big data for language, we want to apply it to a more grounded setup where we have sensor data that a robot will see. And I actually feel like in terms of scale, autonomous vehicles might be one of our best shots at collecting large scale, what I would call 4D data. Because we can get sensors that capture 3D, but over time, so we get this fourth dimension. And the claim is just like we're trying to, we've seen incredibly emergent behavior just by doing next word prediction for language. Maybe we'll see a similar kind of foundational innovation for doing next LiDAR prediction. Okay, so in some sense, what I'll advocate is a view of learning from spatiotemporal data that will make four-dimensional structure first-class citizens. The fundamental thesis is that if we're going to move and navigate and operate in a physical world, then having the 3D structure and technically 4D structure of 3D plus time should be explicit. Okay, So the setup we're gonna do is look, okay, can we try it as a thought experiment? We'll try to make this a bit formal. Let's try to replicate the innovation we've seen for language in sensor data that autonomous vehicles would collect. And at first glance, this is a very reasonable kind of statement. So it's really well known that just like in any data set collection endeavor, typically you're swamped with data and you can only label a tiny fraction of it. So even by modest accounts of the largest scale fleet and capture, such as that data collected either from Waymo or from Tesla that probably have the largest footprint, only a tiny fraction of it will be labeled by humans. And so this suggests that hopefully we can see the same kind of innovative impact if we're able to self-supervise from this data. Okay, so we want to set up a self-supervised task that's sort of analogous to what word prediction is doing. We might do something like this. And in fact, this task has been proposed before, which is next LiDAR frame prediction. So you can imagine we're going to train a network given previous, let's say, T steps of LiDAR. It predicts the next frame of LiDAR or the next T frames of LiDAR. And the reason why this is self-supervised is we can compare that prediction just by, we can just let time evolve forward. We can see how the world actually looked in the future and compute some squared error between the two. And now train a model that will try to predict this. And hopefully, if a model can do well at this, and because it doesn't require any explicit labels, we can train this at scale. And hopefully, if a model can do well at this, it will learn to structure will emerge about how objects move and behave. And hopefully at an emergent scale of the things that we see with large language models and even video models like Sora. Okay, the first thing I want to call out is that actually there's a difficulty, if you, and previous work has done this, but there's a difficulty in doing this, and that is 3D sensor data points are a little bit subtle to work with. In particular, the points that are sensed, if you just think about the physical process, there's a ray that shoots out from the LiDAR sensor and it hits a physical structure in the world. And so one way to think about this is imagine the world is not changing. There's nothing actually happening, but my car is driving down the road. It's very clear that it will look like points are moving, but in reality, of course, nothing is changing in the scene, only the sensor is. So the problem with if you just try to naively predict a point cloud from a LiDAR sensor is what you're really asking the model to do is predict properties of the sensor, which is how many beams do I have? How is the sensor moving over time? But what we really want to understand is the world. That is the fundamental thesis that I'm going to make. If we understand spatiotemporally how the world is evolving, then we can safely navigate. Okay. And so it turns out there's actually a fairly simple way of modifying this, which is instead of asking a network to predict point clouds, we ask this network to predict something like a 4D occupancy field. So one way to think about this is we just grid up the world into X, Y, Z in time, it's 4-dimensional. And for every voxel in the grid, we predict, is there something there or not? It can be a number between 0 and 1. So we can think about this as almost like, if you're familiar with the literature on NERFs, it's an occupancy field. And this is an explicit occupancy field. If you wanted to, you could create the parameters of a NERF that would be an implicit occupancy field. But now the trick that we're going to do now is, given the occupancy field, we will use known sensor extrinsics and intrinsics in the future. Because we know how the car actually moved in the future, we can now render this field from particular sensor positions. And what we get out is a rendered LiDAR suite. And this is pretty easy to do. This is exactly what you do in NERF. You shoot out rays and you see how the rays intersect your occupancy field. And now, instead of rendering an image, we render a LiDAR sweep. And now we can compare the sweep with the ground truth. And so what we find is that this is actually a pretty nice way of trying to have occupancy 4D structure emerge. So what I'm showing here is the ground truth feature. These are two prior work models that actually suggested point cloud forecasting as a task. And in fact, what I'm showing here is a dumb, apologies for the ignorant statement, is a naive baseline that all it does is it just takes all the points that you've seen already, and it just, how do I say this? It's baseline where we take the points that we've seen already, and we just use the, Okay, we use the knowledge of where we're going to be to just show those points. And so this is actually, there's no learning involved. We just take all the collection of points that we've seen. And now when we shoot out rays, okay, now I remember what to do. Sorry, it's a break for a second. When we shoot out rays about where the car should be, we'll just take the closest known point that we've seen before. So the way to think about this ray tracing baseline, it's just assuming the world is rigid. I take all the points that I've seen before, put them into a big point cloud. I know how I'm moving, and so I'm going to shoot out a ray, and I'm just going to grab, I'm going to say, where do I think is the closest point that it's going to hit? So this requires no learning. And this already, if you actually look at the predictive accuracy of this model, it outperforms these learning-based solutions. What we're going to do is something I think a little bit better. We're actually going to predict 4D occupancy, and then we're going to differentially render it the same way you would with an Earth. Okay. And so what's kind of cool about this is that although we've never trained this on any 3D data, we just trained this on LiDAR streams, which is point clouds, 3D structure emerges. And it almost has to, because we're sort of hypothesizing 3D structure such that when we raycast it, it looks like the actual extremes that we think. And so one of the fun things you can do with this kind of 4D model is that you can render it not just from your actual LiDAR intrinsics, but you can render it from a different LiDAR. You can say, well, instead of throwing out 32 beams, let me throw out 16. And you can render what a different platform, a different LiDAR that you would have seen. And so as far as I know, this is what this allows you to do is train on one kind of LiDAR data and test on another. And I guess one philosophy here is, I'm sort of stealing a quote from Judea Pearl, who's one of the godfathers of causality. I had the good fortune of working with him on a grant, and he made the statement that always stuck with me. He said, we should make a commitment to modeling the world and not the data. And so I think that's what this philosophy is. If we just try to predict points, we're really trying to predict properties of the sensor. But in reality, we should really try to understand the world. The world is 4D, it's volumetric. It's undeniable. There's structure, and that structure is changing. And if we make a commitment to model that, we can abstract away the properties of the sensor. So I also believe this would allow for cross data set learning, which is something that, like I said, you could train on one kind of platform, test on another, or maybe you can even train on different platforms. That's probably the more compelling version of this. That we know that training at scale is always this huge enabling sort of property. And so being able to take different kinds of LiDAR and train a coherent 4D model of how the world evolves. I should mention that we've actually held a benchmark competition on this 4D occupancy forecasting. Another workshop yesterday, there was a whole bunch of entries and results. And so I think this is a nice way to kind of formalize this task. We can benchmark it without any labeling, and we can train it without any labeling just by using points. The important thing that you need to know is you need to have point clouds that are also posed. But importantly, we have that for autonomous vehicle data sets because almost all poses are always aligned to a global map. So I think this fits in really well for this differentiable pose perspective. Okay, and then some thoughts that we've kind of entertained is if you understand volumetrically how the world is evolving in the future, maybe you can use this as a cost map for motion planning. So you can then hypothesize different plans for how the ego agent can move, and you try to pick a plan that does not go into any occupied space. And although this by itself, obviously this has no knowledge of semantics. It doesn't understand what the traffic light state of the world is. It doesn't really know if one of these bumps is a person that's moving or a car. But at a first order approximation, it should, this does reveal what the model thinks geometrically where stuff will be in the future. And I think the higher order bit, like that's how we should safely navigate. We should move to places where things, where there's free space. Skip that for the moment. And now we'll talk about some extensions we've done on this. That was just a model where we don't explicitly model moving objects separately from static objects. But the other kind of overwhelming philosophy we see here with this kind of at scale automotive data is that it's also undeniable that 90% of the world is stationary, and then some bits are moving. And of course, the moving bits are the most important, but so much of the world is stationary. Let's actually perhaps build a compositional model So what I'm showing here is some work we've done where we've taken LiDAR point clouds and actually build a model of the static background and moving objects, all without any supervision, just by taking the raw point cloud data. I'll sort of talk about how we do this. And I guess the take-home message is we can basically do the same differentiable optimization again. For the moment, pretend we have initial guesses at poses of the ego sensor and also initial guesses of all the poses of all the moving objects. And now what we're going to try to do is we're going to hypothesize geometry of the rigid world, geometry of moving objects, and motion of the object, such that when we hypothesize them and we know where the ego car is, we then render a sweep. We raycast out rays. We see where the intersection is geometry. And then we look at the rendered sweeps versus the actual sweeps, and we use that signal to drive better models of geometry and motion. And when I'm showing examples here, this is simply doing differentiable rendering on this kind of 4D data. And to actually get this right, I'll show off what I think is a cool but underappreciated property of LiDAR, which is even though almost every LiDAR sweep that has ever been visualized looks like this on the left-hand side, we show a 360 sweep. That is not how the sensor works. The sensor is a revolving sensor. It's a revolving continuous time sensor. And it actually takes roughly 100 milliseconds to sweep all around. And so importantly, what's happening is during the 100 milliseconds, the world's changing. The sensor is moving and then the world is moving. And actually, if you don't model that, that causes incredible amounts of headaches. But it turns out it's actually not that hard to model correctly. So I'll show some examples here. So imagine, so what I'm showing here is the ego car is actually moving that way, moving in this direction. There's another car that's on the world that's moving opposite to that. And you can imagine that basically any sweep that's ever been shown, what a sweep actually is, it's a virtual rendering. You take all the points that were collected from this 100 milliseconds of time, and you say, where would they have been if I had been at if my sensor wasn't moving? So every sweep that you actually ever see is a virtual fabrication. And what that means is every sweep that you ever see has a seam in it. And on one side of the seam were points collected at t is equal to 0. On the other side of the seam were points collected at t is equal to 100, because it took 100 milliseconds to move all the way around. And if you get unlucky, like what we do with this car here, you actually see a person in the car twice, at the beginning of the sweep and at the end of the sweep. So now, if you naively model the sweep as the static measurement, the static shutter, and you try to fit geometry, these 3D or 4D models to it, you bet you fit bad geometry, because you think there's two people in that car, when in fact there's one. In fact, there's other problems that appear as well. So imagine you're driving fast through a corner, and as you're driving, your LiDAR sweep is turning. And what this means is, it could be that by the time you get to this position, you actually see this point on the other side of the building. But now, if you abstract this as a virtual sweep, as everyone does, that was seen from this position, what ends up happening is you end up seeing points behind other objects. And so this causes enormous confusion in the literature. And you'll see lots of papers that try to do various filtering and image processing attempts to try to clean up the data. But my claim is the data is not noisy. It makes total perfect sense if you just model it correctly. And so the solution is we just optimize our neural reconstructions over continuous time. Instead of treating a sweep as a 360 measurement, we treat each slice as a unique measurement. And then we say, where exactly was the car when the sensor is pointed 0 degrees? Where exactly was the car when the sensor pointed at 10 degrees? So in fact, this, by optimizing for, what we can do is we can take the original annotations, ground truth annotations that exist in this autonomous vehicle data sets like UCs. And if you just naively try to take all the points from different time steps for a moving car, align them, and then fit a surface to them, you get really you get really poor reconstructions. If you now optimize for the position of this moving car at every time step, so as to minimize reconstruction error of rendered points versus the measured points, you get a much cleaner looking car. And now, if you actually model the fact that it's a rolling shutter, you optimize for the very precise ego motion of the car at different time steps within a sweep, you get a much more high accuracy model. So essentially what I claim here is that all this machinery for differentiable rendering with ray casting, it works beautifully for LiDAR. And it works beautifully for continuous time measurements. Because we just throw out rays at different points in time. We don't have to abstract this as a sweep. And I should say that we have a paper in doing this that's coming out on archive, and there's also a paper in this conference, NewRad, that does this. And so I think this is, as far as I can tell, this is it's kind of a no-brainer. This is the right way we should be modeling LiDAR data. And one of the things that I showed is that what's interesting is that basically the claim is that you can use this machinery to improve upon ground truth annotation that is provided in these data sets. So in fact, if you take ground truth tracks, these are the reconstructions that you see. And in fact, up here, let's show it over here. This is actually the reconstruction of the world. You take the ground truth background points and align them based on the provided ego poses. So basically, one of the claims here is that we shouldn't actually trust the ground truth that's provided. And in some sense, we should use these kinds of space-time reconstruction optimizations to produce the ground truth. And if we do that, the kind of fun thing is that we actually don't need as much ground truth. So we do this experiment where maybe you only assume labels are provided for moving objects every 1 second or every 2 seconds. Or no labels are provided at all. You just run off-the-shelf detector and tracker. It turns out that does produce the same accuracy as if you had these sparsely labeled sequences. So what this is suggesting is that we can actually do this space-time decomposition of compositional objects on unsupervised LiDAR sweeps. So this is what we're trying to do now, sort of do this at scale. And the claim is like, this is one way of building sort of foundational 4D knowledge. Instead of just predicting points in the next time sweep, we can actually fit exactly how all the dynamic movers are moving and try to predict that information. Okay, so this was all about trying to do 4D reconstruction from LiDAR sweeps, but you can also ask the question, can you do this from RGB images? So let's say you're not Waymo, you're Tesla. And so you have very famously not a LiDAR sensor, but you have lots of RGB sensors. And so we've done a fair amount of work of trying to do 4D reconstructions just from RGB data. And a graduated student, Geng Yang, who's put a lot of effort into producing sort of open source code for doing this. Our hope, and we haven't done this yet, is to sort of make this a version of Nerve Studio for dynamic scenes. But it's actively maintained, and so if you want to try this kind of code out on your own RGB sensor data collected from moving cars or moving vehicles, or even from handheld RGB views, you can go ahead and try this here. So I wanted to show off like a fun visual of what you can do. So talked about reconstructing 4D reconstructions of dynamic scenes from LiDAR, trying to do this for RGB. And then of course, what we really have on an autonomous vehicle stack, we have multimodal sensor data. So another example of multimodal sensors is I actually think we all have them in our back pockets. Your cell phone has a LiDAR sensor, mine does, it has 3 different cameras. And it turns out if you take videos from this, you can also apply the same 4D reconstruction techniques that I talked about. We hypothesize rigid backgrounds, we hypothesize poses of moving objects and poses of the cameras. Given all those hypotheses, we render an image and we render a depth map and compare it to the measured image and the measured depth map. And once we do this, we can actually get reconstructions of dynamic scenes with much higher fidelity because RGB gives us a much higher red signal than the depth. And we can do some kind of cute things. Normally in the world of 4D reconstruction and neural view synthesis, you kind of render things from random viewpoints. What you can do here is just something advantage. We can render from a bird's eye view. This is an indoor scene, obviously. But we can also, because we've reconstructed the motion of, in this case, a cat, we can put a virtual camera on the front of the cat's face and render the world from the cat's point of view, which is kind of fun. We can also put a virtual camera right behind the cat, this blue camera. And because this is collected from a sensor stream of video data that was collected, this is a grad student in his home and his pet cat, we can show the renderings over time. So from this single video stream, the single video plus LiDAR stream, you can fit 4D models and then you can then re-render. And so this is seeing exactly what the cat sees. And this is this little, this sort of blue camera that's following the cat as it moves around. So these are fun examples of showing such reconstructions for other sort of dynamic scenes. So there's just one to show us. I wanted to show these off. So the take-home message here is that I think by fitting 4D models of the background, the rigid background plus dynamic objects, I think this will allow us to learn foundational knowledge that can then allow us to then safely navigate from a robotics perspective. And let me sort of throw out 3 possibilities for these 4D models. So one is use these reconstructions as almost simulators for validation. Very famously, it has been said that in order to bring the safety critical technologies such as self-driving to fruition, we need to validate on 1 trillion miles of data. And right now, no one is close to getting 1 trillion miles from a fleet. And so that suggests we really need to have simulation as part of our validation stack. So maybe we can build models of cities and moving cars by using these kinds of techniques that are emphasized here. The other place where you can use these kinds of 4D models is to train. So once all the fitting, the differentiable optimization that I'm talking about is very expensive. And so you can never run that on a car, but you can imagine doing this on offline data and this very expensive test and optimization, and then take those predictions and then train a fast feed-forward model. This will actually predict deformations of people and cars in a feed-forward way. But the third thing I wanted to talk about, the time that I've left, is using these kinds of simulated models of dynamics to help actually plan for controlling the vehicle. Is Kosher?
Yeah, it's on mine.
Okay, all right, cool. So Kosher, we'll leverage your work quite a lot in this. So the thing I want to emphasize here is new plans. If you folks don't know about it, you definitely should. I think it's a pretty remarkable achievement in kind of taking real world data from an autonomous vehicle fleet and turning it into a full-fledged simulator where you can actually evaluate planning algorithms. So what I wanted to do was talk about it a little bit in a recent method that we have for using these 4D models of how the world can evolve to help better plan. Okay, so first, because people may or may not know about this, but so this data is fairly large scale, 1,300 hours and 50,000 longs collected across different cities, Pittsburgh, Boston, Singapore, and Las Vegas, across different types of scenarios. What we're visualizing here are 6 out of these 80. And what this does is this data is set up as an interactive planner. And as far as I can tell, this is, if anyone else knows of others, please correct me. But usually when we evaluate planning algorithms, we have to go all the way to simulation. So Chelsea was talking about this in a previous talk. So in the AV world, it would be Carla. As far as I can tell, this is the first data-driven simulator for evaluating autonomous vehicle stack, at least the planning portion of it. And so what I wanted to talk about was even evaluating a full planner is kind of tricky. The simplest thing you can do, what this benchmark proposes, is once I finish introducing it, I'll show you what I think are state-of-the-art results on it. But what this benchmark proposes are 3 different ways of evaluation. To give a planner for a robot autonomy, the simplest thing you can do is, if you have recorded logs of how the robot moves in this dynamic world, you could, given the past 2 seconds, give this task to a planner that says, plan out where you want this autonomous vehicle to be for the next 8 seconds. And you can simply look at the squared error between where the planner says the vehicle should be and where the vehicle actually was in the future. So this is called open loop evaluation of the ego vehicle and open loop evaluation of other agents, meaning the rest of the world just evolves as it does in the reported data. What I claim is this is essentially like a forecasting metric that's done for the ego vehicle as opposed to other agents. The next most sophisticated way of evaluation, actually, the next was, okay, the next most sophisticated way of evaluation is, whenever you evaluate this forecaster, instead of always using ground truth histories, importantly, you let the ego vehicle execute its plan, and sometimes it might plan to go off the actual trajectory it was on, and it might end up over here. And so now what you do is you query it with the actual history of where it's been for the past 1 second, and you still ask it to plan where it is in the future. But importantly, the rest of the world still evolves on a rail. The rest of the world still moves as it did the recorded data. And so that's called closed loop ego simulation, but then open loop agent simulation. But the holy grail of evaluation is that the ego agent can move off its path that was recorded in the data, and other agents will now react to how the ego agent is moving differently. So now you have to endow other agents with reactive logic. And so importantly for this benchmark, this first wave evaluation, you can evaluate just with squared error. Your planner says, I want the car to be over here, the car was actually here, and so you look at the squared error. In these other cases, you actually evaluate this as a simulator, where you see, okay, I'm trying to get to my goal state, and either the other agents are on a rail, they just do what was recorded, or they can react to what I'm doing. But then the way I evaluate success is how close did I get to my goal position? Did I run into anyone? Did I, was I uncomfortable by doing high acceleration movements, etc. And importantly, in order to make this thing work, what's really complicated is you have to, this last bit on the bottom right hand side, you have to make agents reactive to, it's almost as if you can joystick control a planner. You can, the way to think about this is you can move the ego car any way you want. And now the rest of the world reacts to how you're moving. And that's what this third option is. You can evaluate a human planner, just letting him play this as a game. Okay, but now what's super important is, well, how does the rest of the world react? And folks may or may not know this, but that's a whole difficult challenge in of itself. But a simple way of handling this is something called an intelligent driver model, which is essentially is a dialogue with very simple logic. I'm showing you all the code here. It's 10 lines of Python code that basically makes other vehicles behave like adaptive cruise control. They will still move along their rigid path, but if there's any other car that comes in front, they're going to put the brakes on so they don't run into stuff. This is what your adaptive cruise control does. So this can be done in 10 lines of Python code. It's not so difficult. You have a target velocity and you have a min gap you want to maintain. You might even see this in your cruise control, how close you're willing to get to the car in front. And you do all this, and there's very simple logic that updates your velocities. Okay, and so this is actually the smart logic that's in these other cars. And now, now that you have this, a very attractive way of doing control, and what I saw in the software industry is essentially trajectory optimization via model predictive control. So what this means is you let, if you're, the way the planner operates is, I'm at a time instant, I observed the last 2 seconds, I'm trying to plan out the next 8 seconds. I'm going to unroll in my internal head how I think the world will evolve. I think other things are going to move in a certain way. And based upon that, I'm going to try to find the best trajectory I can move that minimizes some loss, make sure I don't collide into anything, and maintains comfort and progress toward goal. So this is called trajectory optimization. It's on-the-fly optimization of an internal world model that's unrolled. You can think about this as something like, this is what AlphaGo does. If you're trying to unroll possible moves and say across all those moves, what is the best one I should do? Okay, so this is how I think a lot of autonomy stacks, in particular, classic planners operate. In fact, there was a really incredible piece of work by Poshit that showed that for this planning task, very classic, actually running the IDM logic that we use for other agents, running that as the planner for the ego agent is very simple, essentially 10 lines of code, outperforms all learning-based solutions. So people try Lang GCN, Urban Driver, and actually I should be that right. So IDM actually is what I just said. IDM performs really well. That performs all the other learning-based solutions. And then Kosher had this wonderful piece of work that said we can actually improve upon IDM. And in fact, what the improvement was actually you actually refine what I'm saying. This actually, my claim is, and I don't know if Coach would agree, but we should think about this as model and control. Instead of actually running simple IDM logic for the ego vehicle, what you do is you try to unroll the world forward for 8 seconds. And you want to unroll the world forward in such a way where you predict what everyone else is doing. And then I'm going to evaluate different IDM policies for myself. I'm going to have different target velocities and different mid-gap distances. And I'll see which one of those, when I unroll myself in the next 8 seconds, minimizes the loss, make sure I don't hit things. Importantly, this has no learning involved. And so this does beat everything else. Okay. So this was kind of I think a very frustrating and surprising fact. And I think this is one of the reasons why that, at least for deployed planning, we haven't really seen sort of learning take over. I think there's a lot of learning in early parts of the robot stacks during perception, but for planning, we still have these classic model control methods. So what I'll show is some work that Arun's been doing. It's in the back of this room here that actually shows that you can beat this using a bit of learning, and it's actually leading into this model as a control story. So the solution is, or the observation is, that if you actually look at how people behave in different places, let's say you actually look at how agents in recorded data, what is the typical mid-gap distance that Pittsburgh drivers give to their lead vehicle? And what we find is that it differs per city. So in Boston, people tend to drive a bit more aggressively. They have a slower min-gap to the lead vehicle. And this idea that people have different behaviors in different locations is not novel at all. In fact, there's a very well-known in Pittsburgh and CMU, something called the Pittsburgh left. If anyone here is from Pittsburgh. So what happens is if you go to an intersection, what other cars will do is, if someone's trying to take a protected left turn, for whatever reason, it's customary that when the light turns green, you let the first person who's waiting to take an unprotected left go. And if you're not from Pittsburgh, this is really unsettling. All of a sudden, it seems like someone's going to run into you. So the argument I'm trying to make is that there are very, cultural varying behaviors, and you actually see it in the data. Here, there's just this one based on min-gap distance. Certain, for whatever reason, the running theme is going to be Boston likes to tailgate. They have a smaller mid-gap. And so what that means is, what we can do is, when we try to simulate the behavior of other agents, we can actually optimize for these different parameters in my IDM controller, so as to make sure that when these other agents move with this control logic, their final movement looks like the actual movement in the recorded data. So what I'm doing here is I'm actually trying to fit a better simulator for all the other agents. And I can do it per city. And what you find is that in Boston, you're trying to fit smaller min gaps for your IDM. So Boston drivers should be modeled with IDM controllers with smaller min gaps, so that when you actually unroll them, they tend to tailgate more, as they actually do in the real data. And you can now optimize these parameters over an entire city. So for all the training data for Boston, what is the best set of parameters? You can do this for a particular log. You can even do it for particular agents. So it could be that certain people in Boston, this particular person you observed is driving really aggressively, or this particular person was driving really timidly. You can just fit that. So once you have this data that's fit to these control parameters that are fit to every example, the claim is that you can now, in a model predictive control setup, unroll that logic. When you internally unroll, how do I think the world's going to evolve? Well, because I know I'm in Boston, I'm going to make sure that all the other agents use a small min gap, because I know Boston drivers tend to tailgate. And so what I'm showing here is this is the ego agent moving over time, and both of these were initialized to the same initial state. But what happened is this is the internal model of how the ego agent thinking world's going to evolve. If I endow all my other agents with Boston logic, they follow each other really closely because they have small min gaps. But if I give them normal min gap logic, they don't follow each other closely. So the idea is that I can just do the same model of control. Let me unroll how I think the world's going to evolve and then plan accordingly. But the problem, though, is how do I know what control parameters to use? So one simple answer is, if I know that I'm in Boston, let me use my Boston control parameters. And actually, that works pretty well. It turns out for the new plane competition, you're not allowed to know what city you're in, just given a little history of data you have to go plan. And furthermore, I also argued that not all Boston drivers tailgate. So certain people might not. So what we do instead is we train a classifier to predict the IDM parameters of each agent given its history. So essentially, the intuition is that over the past, I think to some degree you might do this when you drive. You look over the past couple of seconds of how people are driving, like, oh, this guy's a little aggressive over here, this guy's a little timid. And so that I'm going to use when I unroll in my head the world, my model of how the world's going to evolve. I'm going to say, oh, this guy's going to be timid, this guy's going to be aggressive. And I'm just going to use that mental model to then optimize for my trajectory. So essentially, the trick is we take very similar architectures for predicting future agent trajectories, but instead of actually predicting X, Y, Z locations in the future, we predict parameters of controller, the parameters of an IDM controller. We predict what is the min gap that this guy is going to use. And once we use this, we just use that unrolled model in this model as a control algorithm. And so here's some visuals of, if we try to take all this data from our training set and we fit these parameters, this is sort of TSNE. So what we generally do find is that a lot of behaviors, IDM parameters are fit per city. So Vegas tends to have one set of parameters, Boston tends to have others, but there is overlap. Some individual logs and some individual agents, even in some Boston driver is timid, and maybe behaves more like a Las Vegas driver. I'll say this for a moment. And so basically the end conclusion is that we can do a form of model with control where we make predictions about how these agents will behave, and we can reduce error by a fair amount. So one thing to note is that once we get to, so C3 is this final metric, I think the real big take home metric when you evaluate the world in the simulator. And we only have, there's 100%, this upper bound performance, and we only have 6% error, and we can reduce that to 4% by using these adaptive behavior models. And we can ask a slight variation as well. So what happens if we had ground truth behaviors? What happens if someone told us you're in Boston, use the Boston behavior? Or if someone even told us this driver is aggressive, this driver is timid, use a particular min gap here, min gap there. And you get slightly better. So what we're actually saying is that you can actually predict with fairly high accuracy the aggressiveness of individual drivers, these control parameters. Even if you have the ground truth, you don't get that much better. Here's some sort of fun examples of this in action. So here's our ego agents moving down. And then if you do the traditional model blitz control, you'll see this in a sample when it comes back again. You end up running into the car in front of you right here. There's a collision. But here, by better modeling the individual aggressiveness or passiveness of each agent in this log, you end up selecting a better plan that forces you to slow down and avoid hitting the car in front. There's other examples of the log. There's also examples of by better modeling the other agents around you and then predicting a plan as a result of that, you can much quicker get to your goal waypoint. It's a green dot. And you can do sort of fun things where you can train these behavior models on all cities but one, and say if you just train on 3 cities, how well do you do on a never before seen city? Because it seems like some of these behaviors are city specific. Turns out you don't lose that much either. You still see a win. So essentially, it seems like this notion of predicting control parameters for behaviors is an effective way of performing model control. Okay, so maybe I'll sort of kind of summarize here. So the take-home message here of like how do we sort of towards a pathway for full foundational robotics for self-driving. One bet that I would make is that understanding how the world evolves is going to be a first-class goal. So building 4D models of how the world is spatially structured and how that spatial structure evolves over time. And we can do it using these sort of self-supervised tasks where we model occupancy explicitly. And in order to model occupancy explicitly, we can even do a bit better by modeling the individual properties of the sensor including the fact that it revolves. And that allows us to build even better models of geometry and occupancy. And given all these models, if we really understand how things can move and change over time, then one way we can incorporate them into final algorithms for autonomy is we put them inside model predictive control algorithms. And now we have we can use very smart estimates of how we think the world can evolve and how we build these behaviors. And this actually translates to improve performance on some benchmarks. We'll call it this. Okay. Any questions? Yes.
And then for the last PC controls,
Yeah.
you mentioned the IBM strategy is mostly the best with the few new.
Yeah.
But that was more about like following the lane. What about like lane changes and lane cutting? That also embedded in the IBM or not? Like, because you don't drive straight all the time.
Yeah. So the way the IDM logic works is that it needs a reference path. And so, okay, so there's two versions of the IDM. So if you have access to truth features of other objects, so when you run this as a simulator, you can actually look at those, like cars transfer lanes. And so what the IDM logic does is it will follow the pathway of the car acts. If it changes lanes, it's going to change lanes, but it will still do it with sort of this automatic. It's going to look for things in front and avoid hitting it. This is logic used for the reactive metric. Does that make sense? Okay. Now there's the other question of, okay, that's the metric. But how do I do the internal world model to control? So there, I need to figure out, what is the reference? Yeah, because the IDM is not that fancy. It's just following a path and making sure not to hit something in front of it. So the way you get the reference path is actually, Arun, do you have an answer for that? How do you get the reference path to the other agents?
So there we put like a constant velocity.
Yeah. Yeah, so I think that answered it. So there, for the other agents, we don't model them as lanes, at least for the internal order model. We're just saying you're going to keep going as your constant velocity, but we at least make those other agents smart enough where they'll slow down if something's in front of them. So you're right. We're still not really having that rich of an internal world model. And so I guess one more of the story here is it actually feels like model control is a nice setup, and it is kind of a workhorse for autonomy. And basically putting just more smarts into how the world can evolve is actually seamless. So with the original work that the PDMC did is just, it made those agents not reactive at all. They just move forward with constant velocity. So all we're saying is, okay, you can do that, but then make them so they don't run into stuff in front of it. And that by itself gives you a win. Just gives you even more. If we can actually understand, this agent feels like they're going to turn to this. And so I think that's where it's kind of linked to this first two pieces of work and how things evolve, how people behave. Then that I think are models for model control. But right now, I think the thing that's limiting us is almost the general theme of machine learning these days is scale. Like we don't really have high quality behavioral data sets that are annotated. And so that's why the bet that I want to make is we can kind of self-annotate. We still don't have a lot of data. We definitely don't write our speech like we have trillions of words. But we have about 2 orders of magnitude, 3 orders of magnitude less than that. But at least that data we still don't have fully. I think we can by applying these like 4D models.
Thank you.
Yeah. Yeah.
And regarding the 4D foundation model, the zero model is well, like that's.
Yeah, that's a great point. So importantly, class agnostic. But the way to think about it is that it's in the data. So I'm hoping classes might emerge in the same way that if you just train next word token prediction, incredible stuff seems to emerge. If we're just trying to predict where things will be in the future, in the data, I think it's true that smaller things don't move as fast. They tend to be people faster. So it could be that somehow in the learned model, it's internally reasoning about some sort of emergent semantic. But I clearly don't have look at that.
So have you tried like different situations, like indoor dynamic situation?
Yeah, that's
the outdoor.
Oh, that's a great thought. So the thing that we haven't done really is train this at scale. Because, even though I try to advocate, okay, the labels are what's limiting us, so we can kind of self-label by fitting 4D models. But in reality, I think the data is limiting us. So right now, in terms of publicly accepted data, if I was still working in a self-driving company, this is what I would want to do. I would say, give me all, which we don't have annotation. I just want to fit models of how everything is moving. That is going to allow stuff to emerge about how people do move and behave. I don't know if you guys are interested, we should
Yeah.
try to do it.
I can have a follow-up question.
Sure.
Did you try like predict the color light point?
Interesting. Yeah, because you do have some reflectivity from LiDAR.
Yeah.
Yeah, that's a great thought. We have not, but I think that makes a lot of sense. If it's another signal, so why not, let the model try to fit to it?
Yeah, you have image. Maybe we can predict the future images or we can predict the color of light point color.
Oh, I see. When you say color, you mean RGB?
Yeah.
Yeah. I mean, that was like this. I showed a little bit of that with this kind of cute example of this dog. That was color plus LiDAR.
Okay.
And then it's your phone has technically this is LiDAR plus an RGB camera.
Okay, cool. Maybe
Yeah.
final question?
Okay, so I guess real world with like solid objects, whatever.
Yeah.
I was kind of wondering like what you would think about like, okay, let's say you have a robot that has like a very set of like sensory inputs that like you don't really like have like a real representation of, but then it's continuous somehow. So from that, like try predicting what all these kinds of what is it? I guess like what's it called? Inputs are gonna end up becoming. Do you think like work the same way, or is there like a kind of a need for this to something that's physical?
Yeah, I mean the claim. I go back to the kind of the quote from Pearl. Model the world, not the data. So of course the world is physical. It's undeniable. There's 3D structure, and as we move around the room, that 3D structure is evolving. So no matter how we sense it, be it tactile or radar or LiDAR or RGB, the world is the world. So I wanted it. Moral is that it feels like there's a win to be had in trying to abstract that away, the sensing of the world from the actual physical world. Because now you can generalize, maybe train on more scenarios. Yeah.
Okay. Final question.
So I saw you want to make a similar validation and for the training.
Yeah.
So do you think like 4D reconstruction is most important part to make a simulator? Or do you think other parts of the system?
So it seems like in the context of what would it take to make a real photorealistic simulator of the world? Great view synthesis results, nerves, and you go to all these workshops like multi-views. The thing that we don't really understand is behavior, like how things change over time. And I think it's because we don't have data. And so that'll be my bet. It's almost like the behavioral aspect of it. It's a real thing that's lacking. And the best take I would have on that is like, let's start by trying to scale on that. Because the scale seems to be profoundly important.
So how can you be?
Yeah, so I mean, that was sort of the philosophy of, okay, well, first let's try to self-label. Requiring, at least right now, if we only train behavior models from annotated data, that already restricts ourselves immensely. If we learn from unannotated data by self-label, several orders of magnitude of data. That's probably still not enough. I'm saying like that's still nowhere close to what the language word people learn on. But one benefit we do have is that the data that we do have is way more. Like the 3D points are incredibly, like I think they're even more structured than images. So go to trillion scale to get reliable models of how. But that's a hypothesis. I think it's clear that up.
But I think like the company already have scalability. So
Yeah, you're right. So yeah, on the walls of company, I would want to do. This is what I would do. I would say do self-supervised learning, try to self-label all that data, and then try to learn large-scale behavioral models.
Okay. If you can Okay, here comes our final talk. Professor Remina has introduced a lot about the activities that you can program.
Oh, I'm back.
Oh, sorry, I don't need to. Okay, our final talk will be tutorial on nesting and dragout and it will presented by Kashao and Chonghao Sima. Chonghao Sima is a researcher from OpenDrive Lab at Shanghai AI Lab, and Kashao Chita is a student at the University of Tübingen, Germany, where he is part of the autonomous vision group led by Professor Andrew Skager. And Chonghao can start first.
Yeah, hi everyone. My name is Chonghao. So today I'm going to give a joint talk with Kasha about the end-to-end driving language. Kasha, if you can say hi to the room, yeah.
Yeah, hello. Unfortunately, I couldn't be there today, but yeah, looking forward to a good talk.
Yeah, cool. So let's start with a brief introduction of what is end-to-end driving looks like. So as Otos, we need to get things hands-on. Yeah. So now there's many challenges in terms of driving. So the driving system needs to handle various weather, illumination, and different scenarios. And this is very tackle into a module-based design, since there you will always face so-called corner cases by or say as a long tail questions. And usually the driving system involves three parts. The perception part will allow you to see what are around in the scenario, basically of the detection in the 3D world. Then you need to have a prediction module. Tells the ego vehicle what are the other vehicles will do in the futures. Any module that will tell what about the ego vehicle should go in the futures. And basically, there are two ways to do driving system. So one is the so-called classical approach. Another one is called the end-to-end paradigm. The classical approach will be like, okay, we do the perception, prediction, and planning individually, and with some human design patterns linking them together. So the perception and prediction, they will be linked by a bounding boxes, usually a 3D bounding box. So they would work in a 3D manner. And then for the prediction and planning, it will be the ego vehicle or other vehicles trajectory, usually a waypoint in the future. Two modules. But now people are more like, at least the research community are more fancy about the end-to-end paradigms. So like we have and all the modules are connected with the gradient descent rather than the human design patterns to optimize for the final planning tasks. So so now as we define the end-to-end driving system as a raw sensor input, as raw sensor data as the input, and produce a planner or how a low-level control action as the output. Modules can be optimized via gradient descent. That's what we think is looks like. So so what's the advantage of doing this? So there are pretty much advantages like end-to-end manner, like okay, this is simplicity in combining a single model that can be joint training, so you don't need to figure out corner cases at each stage. And also you need to you have the advantages like preventing the cascading errors in module design. So you don't have if there are some errors in the perception task, it won't affect to the planning part. And so finally, the whole system will be directly optimized towards the optimal task, like the self vehicles trajectory prediction. Also, we call it as a planning as for the driving system itself. And so we would like to give briefly introduction of how DriveLM works. We will combine the end-to-end driving system with the visual language models, which is very prevalent in nowadays. So so first let's assume of the driving take a look at what about the vision language model do in the robotics or in body AI fields. So first of all, many papers nowadays in the robotics field, they use a vision language model to do the low-level control directly with a vision language model. I know this is not very intuitive because how can a vision language model do output control signal? This is not intuitive by directly mapping the language output into this discretized or number-based action signals. So how people do that is basically like the answer VQA task that is about answer and action. Action here I actually refers to the this discretized action signals. So when we have some those kind of VQA tasks, then we use this VQA data to tune the with a redesigned tokenizer. This kind of redesigned tokenizer can take handle of the actions that have with the numerics. And then when we have the specific token that predict by the redesign, we de-tokenize those predictive tokens back into actions. So this is very intuitive, but it works really well, as shown in the RT2 or RT series works, like many robotics people are doing real-M in action. So what is good side of this? So it seems to boost the generalization of the model. If you see unseen scenarios before or very complex scenarios with many objects around you, that you can let the VLM itself do the reasoning and to predict the actions. But also it pops out some questions in this paragraph, like is this the right way to open the language toolbox as done in the robotics for the autonomous driving? Because it seems like autonomous driving, it doesn't need the human to interweave with the system. So involving language seems like not necessary. So there are 3 points we think we can answer to these questions, like why we need a language here, because language we think is a generalized and interactive tool for the human to interact with the autonomous driving system. So generalization is about, okay, the vision language model is portraying on the web scale data to be very generalized around the world. What do I mean by generalized? It means that you see many objects that is not familiar it is very familiar on the website. So also there are some regional or global representation requires some kind of explainability about the system. We think that interacting with human through language is a kind of explainability for the human to better understand how the driving system works. And also there are some recent success in the vision language model, like it seems to be very good at reasoning around the world, and then do some visual in context learning. The model itself can understand what it's doing and how to put the vision language model in autonomous driving system. Like it fits the system well, and then it could help the system to boost some ability in the generalizations. So this is a kind of glance of our work. So maybe we don't have too much time to describe. As we said before, the autonomous driving system has three parts: perception, prediction, and planning, and we do the data annotation for these 3 tasks, and this will construct our VQA dataset for driving scenarios. And we trained the model on it, and we found that it does have some generalization across different datasets. Like we train on the Nielsen dataset, and it has some generalization on the Weibo dataset. And we also do this model on Carla, and the Carla things like we have some unseen scenarios, but the model still perform very good in those unseen scenarios. I might go back to the hands-on part. So get in the detail how such a things get evaluated in VQA tasks get evaluated in the driving scenarios. Because this is not the same as the general VQA task, because as you might know, the general VQA tasks, they usually use the MMMU or MMLU things, which are multiple choice. They just need to evaluate if the answer is at a choice level. But in driving scenarios, we have so many objects around you, and those objects will have different behaviors in the future, and all the things are with uncertainty. How do we evaluate such uncertainty, and how do we extract the useful for the later part of the system? So so still we will go with the perception, prediction, and planning paradigms. So for the perception part, we adopt the general idea of the object detection into the language evaluation part. So say like what the question will be, what the objects in the scenarios, and the GT answer will involve several object description of the objects, and then the predict answer will maybe cover one or more of the objects. But if it doesn't cover all the objects, we will use or a Roseline or a Cedar. These are very common language evaluation tool in the NLP rules. Basically, you can see it as a form of the IOU metrics in the language domain. So if you cover as much as possible of the object described in the class, you will get a higher score. So this is the rough idea how we handle the uncertainty in the perception task. Then we also have some multiple choice design. So this is to ask the model to on the current scenario, like are there barriers in front of the ego vehicle or not? Factual track of the physical world. So this time the things goes easier because we just have yes and no as the accuracy to measure the performance. And also we have some multiple choice on the future status of ego vehicle or other vehicle. So this time we also do it as a NLP style, like we have the choice to the model, like what is the future state of the ego vehicle at a specific location, and then if the answer the same with the GT one, and then we will give given the correct, then otherwise it is the false answers. And these are for all the previously QA, these are very easy to evaluate. But for the prediction task, because the task we need to evaluate what the other vehicles do in the future simultaneously. At this time, we think this is not as easy as perception of or factual track of the future state. You need to imagine that if the future state of the other vehicle is the same as we use the human annotator to annotate. So at this time, we involve something called the ChatGPT score to evaluate that what is the similarity between the ground truth score and the predicted answers. Yeah, sorry, I go this way. So when we use the ChatGPT scores, given a prompt like we will give a prompt like we'll give you a question and a correct answers. You will need to measure the similarity between these two answers. And I know for now ChatGPT is a not very great tools that fully rely on it on the correctness of the answer. But when we come to it's varying because they have different words and different kind of saying of the same meanings. At this situation, we think that ChatGPT for now is the best tools to use to measure the uncertainty in those underlying in those answers. And for the final score, we will do a weight sum of all metrics I said before to have a final score of the model. And for now, we think that this kind of rebalancing system is good to evaluate or VQA model or BLM model is having good performance or not in the driver. And Kashyap, I will give the time to you so you can share your screen about how we actually evaluate the what can I say, the trajectory. Yes.
All right. Let me know if there's some problem with the audio or the screen share, but you should currently see a slide from me.
Yeah.
Cool. So yeah, thanks for introducing RivalM, and yeah, I think like the thing I'm going to talk about now is how to evaluate trajectory outputs by these big VLMs. This is extremely challenging because Deva also mentioned it in his talk. There is not really a straightforward way to evaluate driving performance without a simulator, and putting a big vision language model in a simulator is not trivial. So I want to illustrate this with this simple example here. You're in this scenario where I have projected 3 different trajectories onto the image of a vehicle which is approaching a red light and slowing down. The green trajectory is what most people would think is the best of these 3 as a behavior to do in this situation. But it turns out that if you measure displacement errors, which is what most benchmarks currently available for using something like a VLM and checking how good it is at driving do, you will see that the red trajectory, which actually is veering off the path and colliding with another vehicle, gets a lower displacement error than the green one and would be considered better. And this is because the point at which the driver slows down in the ground truth, which are these gray dots, is different from the point at which the model being evaluated decides to slow down, leading to displacements between the predictions at specific time steps. And even though both of these trajectories are maybe equally correct, there is a large displacement error between them. So what about simulation? We do really like simulators in our research, and this has been helpful in developing a lot of models and ideas, and things like NuPlan and Carla are really great. But the biggest problem I see with simulators is that they're extremely compute hungry. You need to actually provide new input information to your driving model at every time step. And this makes them sort of inaccessible to labs with small budgets and not much compute resources. There's also to compound the problem of the compute, there's quite high variance between results in simulators often. If you retrain your model, you can get scores, like in Carla in particular, on a scale of 1 to 100, you can get a score difference of 20 or 30 points for a different training seed of the exact same model. So this makes it very hard to make statistically significant comparisons in simulators. So what we use for benchmarking these VLMs is something called non-reactive simulation. I'll go a bit into how exactly this works. So normally in a simulator, you have a vehicle that makes a new prediction at every simulation tick. So this is what I'm going to visualize on the left here in an animation. The green line is the output of a policy which is driving the red car on this road. And you'll see that this green line changes at every particular frame of this animation. The green line is always centered at the ego vehicle, and it keeps changing. This is ideally what you want to do, but the difficulty of doing this is that you need to give the policy a new input at every simulation tick, which requires simulating sensor data if you want to evaluate a VLM. So this adds a lot of computational overhead, and also there's really not that great simulators out there that have very realistic graphics right now. So what we do instead is make the ego policy non-reactive. Here what you'll see is that in the exact same situation, you have the prediction made by the policy in the very first frame. And we're going to roll out the entire simulation while holding this particular plan static. So we're not going to give the policy a new input at every frame. And so the green line is not going to always be centered at the ego vehicle. You can watch that here. So you can see that the output of the model doesn't change in every simulation frame. You just have a single output and you run your entire simulation of the single output. This is obviously like something that creates quite a lot of differences to the standard reactive simulation. So first of all, you don't observe any states outside your original data distribution. The only ever input your model gets is one of the frames in the data set, which is the first frame in this particular case. But while that makes the task easier for the model also has extra challenges in this setting because it isn't allowed to replan or account for potential problems in its long-term plan, which would be possible in the reactive simulation. Basically, in this setting, once the model has made a prediction over 4 seconds or 8 seconds or whatever your simulation horizon is, it can no longer adapt this prediction and it needs to be much better at long-term planning. So that is like one of the differences of this style of simulation. The other trick we do, which further simplifies and lets like these VLM style models be evaluated, is we make the background traffic non-reactive. I will not go over this in detail because they were mentioned in the previous talk. But the basic idea is that instead of using something like IDM to make other vehicles reactive, you can just let them behave exactly as they did in your original dataset recording. And this leads to weird effects, like you see this blue car driving through the ego vehicle, but it simplifies the simulation environment to a significant extent that it is still useful in creating an interesting benchmark. And now that we have a simulation which is extremely lightweight, so we've removed both the sensor simulation and the traffic simulation aspects, all we need to do is simulate sort of a bird's eye view representation of the ego vehicle. We can actually measure metrics that we care about in the simulation. So we don't need to use displacement errors anymore. We can check if the vehicle under this non-reactive simulation paradigm is colliding with other vehicles, staying on the drivable area, and so on. So I quickly step through like 5 metrics which we currently use. We see if there's a intersection between bounding boxes with the additional check that these intersections are due to error in the ego vehicle. Because like you saw, since we have this non-reactive simulation, we don't want to penalize situations in which another vehicle runs into you from behind, for example. So we need some heuristics for this. We check if we're staying within the drivable area. We kind of have a penalty for near collisions by just making sure the time to colliding is sufficiently large given a projection of the current velocity. We want to make progress, so we don't want to get stuck, and we have a metric for this, and one for having sufficiently low acceleration jerk values. And if we go back to the situation I showed in the very first slide, you can see that like having this diverse set of metrics actually properly captures the different things that are going on with these 3 trajectories in this scene. So you can tell that the orange one is involving a lot of acceleration, so it's not comfortable and goes off the drivable area. The red one has a collision, and the green one is actually a safe driving trajectory. So all these metrics range from 0 to 1, and we have something that looks complicated, but basically a simple way to aggregate them into a single score, which we call the PDM score, which we use for benchmarking these models. I'm going to skip over this in the interest of time and talk about some of the things we did to also make these tools for benchmarking more accessible. The first was that we found that the data sets you have out there for evaluating or training end-to-end driving models are seldom like possible to actually work with because of their huge size. So NuPlan, for example, has over 20 terabytes of data. We subsampled this to the typical frequency that these end-to-end models use, which already reduces the size a lot. And we released this, it's called OpenScene. We further sort of created like standardized train and test splits by improving the test distribution to filter out very simple situations. And once all of this is done, there's like a very convenient 300 gigabyte download for you to start working with. So I quickly mentioned what we do for this filtering. We observed that in the original new plan recordings, and this is true of almost any driving data set out there, some very trivial baselines or heuristics, like in this case, driving straight at a constant velocity and constant heading, actually solve most of the scenarios in the data set really well, because most driving data is inherently quite boring. There's not much interesting stuff going on. It's also visualized in these plots here. If you look at the original new plan data set, these are histograms of where the endpoints of the trajectories are in terms of the X and Y projections. Around like a quarter of the data set, you're standing still, and there is like a drop off of going at higher speeds. But the most interesting thing, and here it's on the log scale, is that around 80% of the data set, you're driving straight, and there's very little data, less than 1% of even having a 2-meter shift at the end of the trajectory. So we filtered this using like quite straightforward heuristics. I'll skip the details, but this significantly improves the distribution of turns and the speed distribution over the data set. We also set up this very standard interface with a like task that is well aligned with what state-of-the-art models do today, and uses or provides access to inputs that are quite standard for driving algorithms today. And using this, we set up a little leaderboard, and we had a challenge that was also like part of CVPR workshop. We saw that like lots and lots of diverse ideas were submitted to the benchmark because it was like really easy to submit, and you don't have this huge simulation compute bottleneck that you have with a typical reactive simulator. The interesting takeaway, or one of the interesting takeaways of the challenge, is that the top solutions, and actually many of the solutions, started using foundation models. So we had the winner using these big VIT large models, which are trained with like depth-based or object detection objectives. And the second place solution was a vision language model, much like the DriveLM model presented by Chonghao earlier. And using this NavSim, which is our non-reactive autonomous vehicle simulator, really simplifies the benchmarking of these models and makes it so that you can do meaningful comparisons between them. So with that, I would like to end my part of the talk. And yeah, thanks for listening. Happy to take questions.
Thank you. Do you guys have any questions? Okay.
Coming, and let's end
Yeah.
up for today's tutorial. And any more questions, feel free to email us or to talk about offline. Thank you.
Yeah. Thank you, guys.
Thank you.